superiority in dense coding through non-Markovian stochasticity, which is with Professor Aditi Sinde and
Sorry,
my
could you
collaborators.
remove black boxes on your screen?
Oh, sorry. Yeah.
Yes, there are two black boxes. Yeah.
Okay, that helps.
Okay, now it is being removed.
Okay, so the talk will be divided primarily into three major sections. Okay, so in the first part, I will give a brief introduction to the quantum dense code, as there are many people who are not from quantum information theory background, following by the scenario when environment comes into the picture and how the capacity of dense coding changes in accordance. In the final part of the talk, we will mainly focus on what we have done in our paper. Okay. So, so the story of the dense coding protocol goes like this. Okay. Just imagine that you and your best friend stays at distant cities, which is quite common nowadays. Say your best friend meets her date at some place, and now after the date, she wants to tell you about her dating experience, right? So the first two things that comes into first two questions that she wants to tell you, that the questions are: is he tall or short, or is he funny or not? Say tall is 1 and short is 0. Similarly, funny is 1 and not funny is 0. Then she can convey the answer to these questions using 2 bits, right? So 0, 0, that means short and not funny. 0, likewise 0, 1, 1, 0, and 1, 1. So basically a 4-dimensional message, right? So what if I tell that using quantum mechanics, we can actually send the message using 2-dimensional, only a qubit, which is 2-dimensional, right? So yeah. So the first paper in this direction. So the first paper in this direction comes in 1992 by Charles C.H.Bennett and Stephen J. Wiesner in PRL, where they showed that 2 bits of information can be reliably sent using 1 bit of entanglement. Okay, so the protocol goes as follows: you and your best friend shares an entangled quantum state, which we call that it is a quantum channel or quantum resource. Now corresponding to the message which occurs with probability pi, say your best friend applies some unitary ui on her qubit. Okay, this is the encoder. So after the after the application of unitary, the resulting ensemble we get is basically pi and rho I. Okay, so then she sends the qubit to you and you do appropriate measurement to decode the message. Now the aim is for which set of unitaries, UIs, and measurement strategies you can extract the maximum amount of information from the ensemble. Okay, for the message index I and the measurement index M, the accessible information from a given ensemble is defined by the maximized mutual information over all the measurement strategies. Okay. Olivo, in his seminal paper on 1973, he showed that this accessible information from a given ensemble is actually bounded by some quantity, which is actually named after him and called the Olivo quantity. And basically, it is a weighted average of the relative entropy of later states rho i's from the ensemble average state rho bar. So it has been shown that this Olivo bound is related to DC, which has actually been much later in 1999 and 2000. The dense coding capacity is basically upper bounded by the maximization of PI UI, which is the which is over the unitaries and the Hollywood quantity. Why Hollywood quantity? Because Hollywood quantity gives the maximization of the, maximum of the information that is available from a given ensemble, and then we want to see, for which ensemble that we get the maximum amount of information, right? So that's why we maximize over the encodings. Okay, so in his paper, Hiroshima showed that this maximum of maximization of PIUI over the, maximization of Hollywood quantity over the PIUI is actually achievable asymptotically. Okay, so for this, if we apply that optimal unitary encodings that is actually orthogonal in nature, and then we can show that this C is actually equals to this quantity. For the, if we apply this unitary encodings, we can see that in this expression, we can see that the capacity turns out to be like this. Okay, so summation of log to di. Di is the dimension of the senders, dimension of the message, and then plus s rho b minus s rho. So s rho b is the reduced system of the the receiver, and s rho is the total set. Okay. So the next question that comes in mind, if we can create a network based on it. So we now increase the to consider this picture where first R sender talks to the receiver R1, and the next n minus R sender talks to the receiver R2. So, and then R1 and R2, these two receivers can actually share, talk using, just by LOCC. Okay, no other means, by no other means. In such cases, the accessible information is actually given by, is actually bounded by this Holevo-like quantity, which is, but the sad part is that this bound is not asymptotically achieved. Okay, so we can only say that dense coding capacity in this case is upper bounded by this, this B2. Okay, so it is not actually asymptotic achievable and not equals to. So there is no such unitary has been found that for which this C rho actually equals to this P2. Okay. So now we want to see what happens when environment comes into the play. When environment decoheres the information from the sent ensemble. The first, let me talk about the cross representation of the open system evolution. Okay, so let's say the system and environment are initially in a product state. So row system tensor product through environment, and the environment the basis of the environments are EK. Okay, and the environment initially is in this E0 state. Okay, so the system and environment jointly, forms a closed state, closed system. Okay, and so because there is no loss of information, this evolution will actually be unitary in nature. And to see the evolution of the system itself, we have to trace out the environment degrees of freedom. And we see this EK, we get the EK row, EK daggers. This EK are the cross operators of the, the evolution. Okay, we can actually see that if we imply this condition that summation EK dagger EK is actually identity matrix, then it will be, and so that this evolution is stress preserving. Okay. Okay, so two of the well-known channels are dephasing channel and depolarising channels, and we'll work with these two models. So it's better to show that what are the cross representations of these two. So this here is the cross operators for the dephasing channel in the Markovian region, and in the non-Markovian region, this gets modified at this, where alpha is non-Markovian parameter. P is the error probability, which runs from 0 to half in this case. In the depolarizing channel, this error probability runs from 0 to 1, and the corresponding non-Markovian version is given by this. But we can see that this error probability actually upper bounded by some, the upper bound is dependent on the non-Markovian parameter, that is alpha. Okay, so if alpha increases, the range of this error probability decreases. Okay. So now we are all set to discuss the noisy decoding protocol. The expression of the decoding in this scenario can be written in this way. That okay, so okay, note that as noise acts on the qubit that Alice sends to the Bob. Okay, so the the entropy of the receiver, that is Bob, cannot change, but the entropy of the total system can change. Okay. Then again, we have to minimize this entropy, this entropy, just to get the maximum amount of information over the unitaries USIs. So we apply the USIs and see if, say that for USI mean, we get the minimum of the entropy S rho tilde. Okay, so this, in this regard, I want to introduce the covariant channels, which is basically a channel, that commutes with the CPTP map. This covariant channel commutes with any unitary encodings. Okay, so for this reason, the unitary, the covariant maps are actually helpful for computational causes, because we don't have to minimize this, because this entropy in this case, okay, these unitaries will get outside, and entropy will be invariant under the unitary evolutions. For the two receiver case, as we have just seen here, as we have just seen here, this okay, so this rho x will change by some, this rho x's will change by some zeta, and yeah, for the two receiver case, the maximum of this here, this we will apply some lambda and just replace that in this in the earlier expression, and we'll get the 2D super case bound. Okay. Okay, so now I will discuss about our work. I will say that the work can be divided into two directions. Okay, first we went beyond the Markovian region and showed that the non-Markovianity helps. And then we introduced randomness into the channel to solve dense coding capacity, which is counterintuitive. So we work with these two, we work with GGHG and GW states. And for two receiver, two sender, one receiver case, and two sender, two receiver case. Okay, so these three means 2s1r, which is two sender, one receiver, and 2s2r for two sender, two receiver. For this, if we put x equal to root over 1 by 2, that will give the GHG state, and that for that the DCC will be maximum. That is the perfect DCC. In this case, for the GW state, we have modified the GW state in such a way that if we put that A is equal to half, we'll see that for the sender is to receiver case, we'll see that 1 qubit of entanglement is there. Okay. So now we'll come to our first result. It says that for a certain range of error probability P, we observed non-Markovian dephasing channel is more advantageous than its Markovian counterpart for n+1 qubit GGAG states. So okay, so yeah, so this is our result. This is our plot. In the figure 1 corresponds to this GGAG state, and the figure C is corresponds to the the figure A corresponds to GAG state, and figure C corresponds to GGAG state. Okay, so we see that for high P, the high error probability and high non-Markovian region, we have non-Markovian advantage. Okay, so where we see that in this region, in this high probability region, probability of error region, there is, for Markovian, there is no quantum advantage, but for the non-Markovian, the non-Markovianity shows that there is actually quite a significant quantum advantage up to 1 decimal places. Okay. We see the same thing for the GGAG state. Here we fix the the experiment. We fix the yeah, sorry, we didn't fix here something. Yeah, for the state parameter X, we varied the X parameter, the state parameter, and also that for different alpha, for increasing alpha, we saw that the advantage is is greater. But for the B, for the plot B and plot D, this plot B is for the W state, and this plot D is for the GW state. For plot B and D, we see that there is no quantum advantage in higher alpha region, because this W state and the GW states are basically very susceptible to noise, and that's why the detrimental effect overcomes the advantage that is seen in the GG state here. Okay. Okay, so our next result basically shows in the case of two receiver for dephasing channel, the upper bound on DC, or that is the dense coding capacity, actually doesn't depend on the noise itself. So non-Markovian advantage can't be seen here, obviously. Okay. However, as depolarizing channel acts on all the three directions, high non-Markovian parameter alpha restricts the range of P, and the dense coding capacity can go to the range of P where non-Markovian advantage is present. So under the depolarizing channel, only detrimental effects were observed. So yeah, so this is the plot for 2S2R, that is two sender two receiver depolarizing channel. So as I have already said, the detrimental effects of depolarizing channel is much higher than the dephasing channel, and that's why high alpha, because depolarizing channel acts on all the three regions, sigma X, sigma Y, and sigma Z, they are acting. So X, Y, Z detection both, and that's why the noise is very, that is very high noise, and that's why the advantage in the high alpha region is not actually seen. Another reason that that because high alpha values restricts the range of the P, that is the error probability, to a shorter range. That's why the dense coding capacity can't go to that region where to that region of P where the non-Markovian advantage is actually seen. Anyway, so yeah, so W and GW states is more susceptible to noise than JJ and GG states, and no advantage in non-Markovian cases. Okay, to come to our most important result, I have to first discuss about the random channels that we have introduced. So yeah, so the motivation is that in the real life scenario, it is very unnatural to anticipate that the noise affecting the resource is of very specific sort of kind. Okay, like pure dephasing or depolarising noise. So we modeled channels such that it is very much like dephasing or depolarising type, but not exactly. What we did is actually replace the poly matrices with some random unitary matrices in their cross representation to ensure that the unitaries are near to the poly matrices. Okay, so we took the parameters, these parameters omega, theta, and delta. This phi is actually a phase, it will not matter. So this omega, theta, and delta are the parameters of the unitaries, and we'll take this we'll take this take the value of these parameters from a Gaussian distribution. We'll randomly choose this parameter from a Gaussian distribution whose mean values will give the parameter values of the corresponding polymatrices. Okay, and the standard deviation will epsilon. The epsilon will define the randomness into the channel. Okay, so for example, if you want to model some unitary random unitary, which acts like sigma z but not actually the sigma z. So we see the sigma z values, sigma z occurs when omega is equal to 2 pi, theta is equal to 0, and delta is equal to 3 pi. We'll take this omega, theta, and delta value in such a way that yeah, so we have replaced this sigma z by uz here. Yeah, so we'll take these parameters from the Gaussian distribution whose mean is like omega is equal to 2 pi and standard deviation is epsilon. Okay, so in this way we have modeled these random unitary channels which are actually CPDP, and we have already checked that. So the theorem that we have found that the upper bound on the dense coding capacity affected by the random noisy channel for multiple senders and single receiver is greater than the capacity influenced by the noise without randomness. Basically, that means that the randomness or the stochastic behavior of this channel actually helps with is helpful for the dense coding protocol. Okay. So yeah. So yeah, for the 2S one receiver dephasing type, 2S two sender one receiver case and dephasing type noise, dephasing time random channels. So here, this is the JG state. This is for the JG state. This is for the GGG state. This is for the W state, and this is for the GW state. Okay, and we varied this epsilon, which is the standard deviation of the Gaussian distribution. We have defined this as the randomness in the channel, and we have varied this epsilon from 0 to 1, and have seen that for increasing epsilon, the capacity is getting increased. Okay, so even when we have seen that for the non-Markovian cases, there is some some advantage than the Markovian cases in the high P region. We have seen that increasing epsilon will get better quantum advantage for this case. Okay. And I have already written here this alpha, that is the non-Markovian parameter, is fixed at 0.8, which is very high. And yeah, so for sufficient high value of epsilon, the capacity doesn't even hit the classical limit. We see that for the W state and GW state, in the earlier cases, we have seen that even non-Markovianity cannot help in this case. But this random channel with greater epsilon, that is greater randomness in the channel, that will actually help. Okay, so yeah, the next result is the most interesting one. This figure is for the two sender, two receiver case, and the depolarizing channel, depolarizing type random noise channel. Okay, so we earlier observed depolarizing channel can incur nothing but detrimental effects on transcoding capacity, but interestingly, a depolarizing type random channel can give better news even in this case. Okay, so alpha is again fixed at 0.9, which is very high. Okay, so with this, so we finally reached to our to the conclusion of the talk. The results can be summarized in this precisely in these 3 points: that the non-Markovianity is beneficial for the transcoding capacity, and the deviation from this from the ideal Pauli channels due to the randomness helps. It is beneficial for the transcoding capacity, and though this non-Markovian advantage is absent for the depolarizing channel, stochasticity of the channel can actually compensate and give a significant amount of quantum advantage. So that is all. Thank you.
Thanks, Abhishek, for this beautiful talk. So participant can ask question or write it in a chat box. So now our session is open for question.
Thank you for your talk. What is stochastic parameter in your?
I mean, by stochasticity, we have actually, we have just said that this randomness in the channel, that is, by stochasticity, we meant that. Okay.
Okay.
For the,
this is
stochastic problem is basically a dynamical thing, but in this case, we have just meant by meant that this randomness is stochastic. I mean, yeah.
Randomness of phase or amplitude. What?
This, one second. Yeah, so this randomness in the parameters of the channel, what we have done that the sigma z for the dephasing noise. Okay, so the cross parameters are what? This I and this, and then there is some sigma z. So we replace this sigma z with some random channel u, and such that this u kind of it is very near to sigma z, but actually not sigma z. There is some randomness, some deviation from this sigma z. Okay.
It's clear. Thank you.
So we have, yeah.
Are there any other question? If there is no other question, so we will move to our next talk. And thanks, Abhishek, for this beautiful talk. And we are hoping to